Welcome to the next lecture of Basics of Control System. In the last lecture, we have seen various types of classification of control systems such as linear and nonlinear system, then time variant and time invariant system, and third classification was linear time variant and linear time invariant system. We have also seen the Laplace transform, definition of Laplace transform, some standard Laplace transforms, advantages of Laplace transform and inverse Laplace transform. In this video lecture we are going to see what is transfer function, then the transfer function of RLC circuits, how to determine the order of control system, system order and proper system, and how to determine the type of system. First is transfer function. See what is transfer function? It is the relationship between input and output of a system, and it is given by the transfer function. And its definition is the ratio of Laplace transform of the output to the Laplace transform of input under the assumption of zero initial conditions is defined as transfer function. Okay, so basically transfer function is the ratio of Laplace transform of output to the Laplace transform of input. So here it is shown diagrammatically. On the left side you can see the system g of t. It is the time domain system. Its input is r of t. Okay, then the system function is given as g of t and the output is c of t. So when we apply the Laplace transform on this system g of t, it is converted to the S domain. Okay, so as we know, Laplace transform converts the time domain function into S domain function. So after applying Laplace transform, the system is represented as g of s. You can see the notation on the left side, that is in the time domain system. It is represented in small letters, while in the right hand side, that is S domain, it is represented in the capital letters. Okay, so the system g of t applies, the system g of t after applying Laplace transform becomes system g of s, and here g is the capital letter represented by the capital letter. Okay, then the Laplace transform of r of t is represented as r of s. Note again, here r is capital. The Laplace transform of c of t is c of s. C is capital. Okay, so the transfer function is given by the equation g of s is equal to Laplace transform of output, that is c of s, divided by Laplace transform of input, that is. Now we will see how to get the transfer function of closed loop system. So in the first lecture we have seen the closed loop system, then how it is represented. Okay, the main blocks of the closed loop system are error detector. The input given to it is the input signal as well as the feedback signal. Here you can see R of S and B of S are input to the error detector. Okay, then after when it is calculated, the process or plant is represented as G of S. Okay, and the output is C of S, and it is fed to the error controller via H of S. Okay, feedback element, here it is represented as H of S. So recall the earlier diagram of the closed loop system. In the closed loop system, feedback is provided, and here the Laplace transform of signals are shown. Previously in that we have taken the time domain functions. Okay, so there was R of t, then C of t, like that, but here we represent by the transfer function. We have to represent the transfer function or in the S domain. So all the notations are in the S domain. Okay, now concentrate on the error signal. So error signal is given by, okay, so as you can see in the diagram, error signal is output of error detector. Okay, so it is given by R of S minus B of S. So this is our equation number 1. E of S is equal to R of S minus B of S. So from this, or rearranging this equation, we can get R of S is equal to E of S plus B of S. Okay, so input signal is equal to error signal plus feedback signal. We can say that. Then the gain of the feedback network is given by, okay, so you can see the gain of the feedback in the diagram is H of S, and it is equal to B of S divided by C of S, where B of S is, yes, feedback output divided by C of S is output of the system. Okay, H of S is equal to B of S divided by C of S. By rearranging this equation, we get B of S is equal to H of S into C of S. So equation number 2 represents the feedback signal B of S. Then gain of the closed loop system is given by G of S is equal to C of S divided by E of S. See the diagram to get this equation. See, G of S is the gain of the system, that is equal to C of S, that is output, divided by error signal E of S. By rearranging this equation, we will get C of S, that is output signal, is equal to G of S is equal to E of S. So this is our equation number 3. See again, in the first equation we represent R of S or E of S, that is error signal. In the second equation we represent the B of S, that is feedback signal, and in the third we represent the output signal C of S. Now we have to substitute the value of E of S from equation number 1 into the equation number 3. See, in the first equation the value of E of S is R of S minus B of S. So we have to substitute it into the equation number 3. After substitution, the equation will become C of S is equal to G of S into R of S minus B of S. So that is the substitution for E of S. Then by multiplying G of S into the bracket, we will get C of S is equal to G of S into R of S minus G of S into B of S. We will call this as equation number 4. Now substitute the value of B of S from equation number 2 to equation number 4. Okay, so in the equation number 2 the value of B of S is H of S into C of S. So by substituting it, we will get C of S is equal to G of S into R of S minus G of S into B of S is given by H of S into C of S. In the next line, R of S is taken common and G of S is into R of S is equal to C of S plus G of S into H of S into C of S. So minus part is taken to the left side, then C of S is taken common, and we will get G of S into R of S is equal to C of S into bracket 1 plus G of S into H of S. Then the transfer function is given by C of S divided by R of S. So by definition we know that transfer function is Laplace of output divided by Laplace of input. Okay, so Laplace of input is represented by C of S and Laplace of input is defined by R of S. So from the equation, it is g of s divided by 1 plus g of s into h of s. So we get this simply by rearranging the above equation. Okay, so to get this transfer function of closed loop system, read again all the steps one by one. There are very simple steps. Only substitution is done to get C of s upon R of s, which is nothing but the transfer function. Okay, so this is about the transfer function of closed loop system. Next, we have to calculate the Laplace transform of passive elements R, L and C. As we know, the resistor, inductor and capacitor, these are the passive elements. The Laplace transform can be used independently on different circuit elements, and then the circuit can be solved entirely in the S domain. Okay, and let us see how it is done. First, Laplace transform of resistor. Resistors are time and frequency invariant. Therefore, the transform of a resistor is same as the resistance of the resistor. Okay, so Laplace of resistor is equal to R of s. Laplace transform of capacitor. Okay, the for calculating the Laplace transform of capacitor, we have to see the relationship between voltage, current and capacitance in the time domain, and it is given by I of t is equal to C into dv by dt. Okay, d into v of t by dt. So it is differentiation of the voltage signal. Okay, solving for voltage, we will get v of t is equal to 1 upon C integration of I of t dt from 0 to infinity. Then transforming this equation into Laplace domain, okay, that is by taking the Laplace transform of this equation, we will get. So as we know, v of t's Laplace transform is v of s. Then 1 upon c is constant term, so 1 upon c is kept at as it is. Then Laplace transform of I of t dt is 1 upon s into I of s. Again, we will solve for the ratio of v of s divided by I of s. Then we will get the following: v of s upon I of s is equal to 1 upon sc. Therefore, the Laplace transform of capacitor with capacitance C is given as 1 upon sc. Laplace transform of inductor. As we know, the relationship between voltage, current and inductance in the time domain is given by V of t is equal to L into dit by dt. Okay, so putting this into the Laplace domain, we will get V of s is equal to S into L into I of s, since L is constant. Then we have to take the ratio, that is Laplace transform of output divided by Laplace of input, that is V of s divided by I of s. So that is equal to SL. So Laplace transform of inductor is given by SL. Okay, so we have seen the Laplace transform of resistor, inductor and capacitor. Now we will get the transfer function of RC and RLC circuit. First we will see how to find the transfer function of the RC network, that is the network having resistor and capacitor. As you can see in the diagram, the input given to the circuit is Vi of t. Okay, there are two components R and C. The current flowing through it is I of t and the output is V0 of t. Applying KVL to the input loop, Okay, we will get, see the input loop, so that is having the components are C, then voltage Vi of t and current I of t. Okay, so applying KVL to the input loop, we will get Vi of t is equal to R into I of t plus 1 upon C into integration of I of t dt from 0 to t. Now we will take the Laplace transform of the above equation. Then the equation will become Vi of s is equal to R into I of s plus 1 upon Sc into I of s. So let us call it as equation number 1. Now we will apply the KVL for the output loop. So in the output loop there is one component capacitor and another is output signal V0 of t. So applying KVL to the output loop, we will get V0 of t is equal to 1 upon C into integration of I of t dt from 0 to t. By taking Laplace transform of this equation, we will get V0 of s is equal to 1 upon Sc into I of s, equation number 2. Okay, then rearranging this equation for I of s, we will get I of s is equal to Sc into V0 of s. So that is equation number 3. Now see the equation number 1. By taking the Laplace of equation number 1, okay, so by taking this, we will get Vi of s is equal to I of s is taken common into bracket R plus 1 upon Sc, and from equation number 3 and 4 we can write Vi of s is equal to V0 of s into Sc into R plus 1 upon Sc. Then as we know, transfer function is V0 of s divided by Vi of s. Okay, so output divided by input, so that is 1 upon Sc into R plus 1 upon Sc. So by simplifying this, we will get the transfer function as 1 upon SCR plus 1. So diagrammatically it is represented again. So on in the block the system is shown, okay, and its transfer function is 1 upon S into C into R plus 1, and its input is Vi of S, output is V0 of S. Now the transfer function of RC and RLC circuits, in that we have seen for RC, now we will see for RLC. Here there are three components: resistor, inductor and capacitor. Applying the KVL for the input loop, see the input loop on the left side, that is having RLC and the signal Vi of s. So applying KVL, Vi of s is equal to R into I of s plus SL I of s plus 1 upon SC I of s. By simplifying this, we will get Vi of s is equal to R plus SL plus 1 upon Sc into I of s, equation number 1. Here I of s is taken common on the right hand side. Then apply KVL for the output loop. As you can see, in the output loop there is one component, that is capacitor, okay, and its Laplace transform is 1 upon Sc, as we know, and second is the output signal V0 of s. So applying KVL to the output loop, we will get V0 of s is equal to 1 upon Sc into I of s, equation number 2. So now we get the equation for input as well as for output. Now we have to get the transfer function. The transfer function is given by V0 of s divided by Vi of s. Simply substitute the values of Laplace of output, that is V0 of s, and Laplace of input, that is Vi of s, from equation number 2 and equation number 1. Okay. So by simplifying it, we will get finally the transfer function as 1 upon s square LC plus SCR plus 1. So this is the transfer function of RC circuit. Okay, next is the order of the system. So we have to calculate the order of the control system. See, what is it? The order of control system is defined as the highest power of S present in the denominator of closed loop transfer function G of S of unity feedback system. Okay, transfer functions denominator is observed, and the highest power of S in that denominator is known as order of the system. So let us see one example so that you will get what it is. Here is one example. Determine order of the given system, and the transfer function is given as G of S is equal to S into S plus 2 divided by S raised to 4 plus 7 S raised to 3 plus 10 S square plus 5S plus 5. As we know, order means you have to see the denominator, and highest power of S is known as order. So in this equation, the highest power of denominator is 4. Hence, order of this given system is 4. Next point is system order and proper system. Highest power of S present in the denominator of closed loop transfer function is known as order of system. We have seen this. Okay. Then a proper system is a system where the degree of the denominator is larger than or equal to the degree of numerator polynomial. So let us explain this by one example. One transfer function is given, G of S is equal to S plus 5 into S plus 2 divided by S into S plus 3 S plus 4. See, to get the highest power, we will expand this. Okay, so that we will get by for expanding for denominator, we will get S cube plus 7S square plus 12S is equal to 0. The highest power of denominator is now 3. You can see S cube means power is 3. Hence, the system is called as third order system, and degree of denominator is larger than the numerator. Okay, if you calculate S plus 5 into S plus 2, the highest degree will be 2 S square you will get. Okay, so see, the degree of denominator is larger than the numerator, so it is called as proper system. Next example, determine the order of the system. For determining this, you have to expand it. Okay, by expanding, that is, in the denominator you have to multiply the bracket by S cube, then you will get 7S raised to 5 plus 12S raised to 4 plus 5S cube is equal to 0. As you can see, the highest power of S is 5. So it is, yes, fifth order system. It is called as fifth order system, and degree of denominator is larger than that of the numerator. Numerator's degree is 1. Okay, you can see S plus 5 term is there in the numerator, so its degree is 1, while in the denominator degree is 5. So the degree of denominator is larger than that of the numerator, so hence it is the proper system. Now, types of system. Okay, so we can determine the type of system depending on the highest power of denominator. So recently we have seen how to calculate the highest power of denominator. Okay, by simply expanding the terms we will get the highest power. Then if the S is having the power 0, okay, then it is called as zero order system. If s is having the power 1, that is highest term in s in the denominator is having 1, then it is called as first order system. And if the highest power is 2, then it is called as second order system. So see the definition of zero order system. If the highest power of complex variable s present in the characteristic equation is 0, then it is called as zero order system. Okay, and it is represented by this, where the transfer function is given as 1 upon 1 plus t. So here is one example. Consider a unity feedback system with transfer function g of s is equal to 1 upon 1 plus t. Its characteristic equation is 1 plus t is equal to 0. It is characteristic equation. It is the equation of the denominator. Okay, so you can notice here there is no s term. So it can be given as 1 plus s raised to 0 into t. So all of us know that raised to power 0 is 1. So s raised to 0 is 1. So you can substitute s raised to 0. Okay. Then here the highest power of s is equal to 0. Hence the system given is the zero order system. And the example of this is amplifier type control system. Next is first order system. If the highest power of complex variable s present in the characteristic equation is 1, then it is called as first order system. So see, what is characteristic equation? It is the equation of the denominator. If the highest power of s in the denominator is 1, then the system is called as first order system, and its transfer function is given as 1 upon 1 plus SCR. Okay, so consider a unity feedback system with a transfer function g of s is equal to 1 upon 1 plus SCR. Hence, the characteristic equation is given as 1 plus SCR is equal to 0. Its highest power of s is 1. Hence, it is first order system. The practical examples of first order system are RC circuits, thermal type systems. Next is second order system. If the highest power of complex variable s present in the characteristic equation is 2, then it is called as second order system. You can see the transfer function given in the block diagram. So it is 1 upon s square into LC plus SCR plus 1. It is the transfer function of RLC circuit. Okay, so its highest power of s is 2. It is called as second order system. Then in this it is explained s square LC plus SCR is equal to 1, where the highest power of s is 2. So it is second order system. And practical examples of second order system are RLC circuits, robotic control system, etc. So let us summarize what we have studied today. Transfer function, that is, what is transfer function? Simply it is the ratio of Laplace transform of output to the Laplace transform of input. Then we have also seen the transfer functions and Laplace transforms of RLC circuits. Then order of the control system, how to determine the order of the control system? Yes, it is the highest power of s in the denominator. Then system order and proper system. Okay, so when it is called as proper system, when the order of s in the denominator is greater than or equal to the order of s in the numerator, then it is called as proper system. And lastly, the types of system, that is zero order system, one order system and order 2 system. So if the highest power of s in the denominator is 0, it is called as zero order system. If the highest power of s in the denominator is 1, it is called as one order system. And if the highest power is 2, it is called as second order system. Okay, so this is for the today's lecture. Solve the derivations again and again so that you will get how it is calculated.